What's up? I am not doing what the description says. I'm just watching YouTube because I'm watching my son. I can't type when he's on me. So, um, how to talk to text on Windows 11. Windows H, that's what I thought. Crash Course Computer Science. There we go. No, that was like a.
You will not believe how much cool
If you want to become a data scientist, Caltech is one university that you should consider because Caltech's reputation is second to none. Learn to make data-driven decisions leveraging Caltech's academic excellence.
I was here.
Mixed up. And this problem only gets worse with transistors changing states millions of times per second. So placing two signals as far apart as possible using just on and off gives us the most distinct signal to minimize these issues. Another reason computers use binary is that an entire branch of mathematics already existed that dealt exclusively with true and false values, and it had figured out all the necessary rules and operations for manipulating them. It's called Boolean algebra. George Boole, from which Boolean algebra later got its name, was a self-taught English mathematician in the 1800s. He was interested in representing logical statements that went under, over and beyond Aristotle's approach to logic, which was, unsurprisingly, grounded in philosophy. Boole's approach allowed truth to be systematically and formally proven through logic equations, which he introduced in his first book, The Mathematical Analysis of Logic, in 1847. In regular algebra, the type you probably learned in high school, the values of variables are numbers, and operations on those numbers are things like addition and multiplication. But in Boolean algebra, the values of variables are true and false, and the operations are logical. There are three fundamental operations in Boolean algebra: a not, an and an or operation. And these operations turn out to be really useful, so we're going to look at them individually. A not takes a single Boolean value, either true or false, and negates it. It flips true to false and false to true. We can write out a little logic table that shows the original value under input and the outcome after applying the operation under output. Now here's the cool part. We can easily build Boolean logic out of transistors. As we discussed last episode, transistors are really just electrically controlled switches. They have 3 wires, 2 electrodes and 1 control wire. When you apply electricity to the control wire, it lets current flow through from one electrode through the transistor to the other electrode. This is a lot like a spigot on a pipe. Open the tap, water flows. Close the tap, water shuts off. You can think of the control wire as an input and the wire coming from the bottom electrode as the output. So with a single transistor, we have 1 input and 1 output. If we turn the input on, the output is also on because the current can flow through it. If we turn the input off, the output is also off and the current can no longer pass through. Or in Boolean terms, when the input is true, the output is true. And when the input is false, the output is also false, which again, we can show on a logic table. This isn't a very exciting circuit though, because it's not doing anything. The input and output are the same, but we can modify this circuit just a little bit to create a not. Instead of having the output wire at the end of the transistor, we can move it before. If we turn the input on, the transistor allows current to pass through it to the ground, and the output wire won't receive that current, so it will be off. In our water metaphor, grounding would be like if all the water in your house was flowing out of a huge hose, so there wasn't any water pressure left for your shower. So in this case, if the input is on, output is off. When we turn off the transistor though, current is prevented from flowing down it to the ground. So instead, current flows through the output wire. So the input will be off and the output will be on. And this matches our logic table for not. So congrats, we just built a circuit that computes not. We call them not gates, and we call them gates because they're controlling the path of our current. The AND Boolean operation takes 2 inputs, but still has a single output. In this case, the output is only true if both inputs are true. Think about it like telling the truth. You're only being completely honest if you don't lie even a little. For example, let's take the statement, my name is Carrie Ann and I'm wearing a blue dress. Both of those facts are true, so the whole statement is true. But if I said my name is Carrie Ann and I'm wearing pants, that would be false because I'm not wearing pants, or trousers if you're in England. The Carrie Ann part is true, But a true and a false is still false. If I were to reverse that statement, it would still obviously be false. And if I were to tell you two complete lies, that is also false. And again, we can write all of these combinations out in a table. To build an AND gate, we need two transistors connected together so we have our two inputs and one output. If we turn on just transistor A, current won't flow because the current is stopped by transistor B. Alternatively, if transistor B is on, but transistor A is off, same thing, the current can't get through. Only if transistor A and transistor B are on does the output wire have current. The last Boolean operator is OR, where only one input has to be true for the output to be true. For example, my name is Margaret Hamilton, or I'm wearing a blue dress. This is a true statement, because although I'm not Margaret Hamilton, unfortunately, I am wearing a blue dress. So the overall statement is true. An OR statement is also true if both facts are true. The only time an OR statement is false is if both inputs are false. Building an OR gate from transistors needs a few extra wires. Instead of having two transistors in series, one after the other, we have them in parallel. We run wires from the current source to both transistors. We use this little arc to note that the wires jump over one another and aren't connected, even though they look like they cross. If both transistors are turned off, the current is prevented from flowing to the output, so the output is also off. Now, if we turn on just transistor A, current can flow to the output. Same thing if transistor A is off, but transistor B is on. Basically, if A or B is on, the output is also on. Also, if both transistors are on, the output is still on. Okay, now we've got NOT, and OR gates, and we can leave behind their constituent transistors and move up a layer of abstraction. The standard engineers use for these gates are a triangle with a dot for a NOT, a D for the AND, and a spaceship for the OR. Those aren't the official names, but that's how I like to think of them. Representing them and thinking about them this way allows us to build even bigger components while keeping the overall complexity relatively the same. Just remember that all of the mess of transistors and wires is still there. For example, another useful Boolean operation in computation is called an exclusive OR, or XOR for short. XOR is like a regular OR, but with one difference. If both inputs are true, the XOR is false. The only time an XOR is true is when one input is true and the other input is false. It's like when you go out to dinner and your meal comes with a side salad or a soup. Sadly, you can't have both. And building this from transistors is pretty confusing, but we can show how an XOR is created from our three basic Boolean gates. We know we have two inputs again, A and B, and one output. Let's start with an OR gate, since the logic table looks almost identical to an OR. There's only one problem. When A and B are true, the logic is different from OR, and we need to output false. To do this, we need to add some additional gates. If we add an AND gate and the input is true and true, the output will be true. This isn't what we want, but if we add a NOT immediately after, this will flip it to false. Okay, now if we add a final AND gate and send it that value along with the output of our original OR gate, the AND will take in false and true. And since AND needs both values to be true, its output is false. That's the first row of our logic. Put false. To do this, we need to add some additional gates. If we add an AND gate and the input is true and true, the output will be true. This isn't what we want, but if we add a NOT immediately after, this will flip it to false. Okay, now if we add a final AND gate and send it that value along with the output of our original OR gate, the AND will take in false and true. And since AND needs both values to be true, its output is false. That's the first row of our logic table. If we work through the remaining input combinations, we can see this Boolean logic circuit does implement an exclusive OR. An XOR turns out to be a very useful component, and we'll get to it in another episode. So useful, in fact, engineers gave it its own symbol too, an OR gate with a smile. But most importantly, we can now put XOR into our metaphorical toolbox and not have to worry about the individual logic gates that make it up. or the transistors that make up those gates, or how electrons are flowing through a semiconductor, moving up another layer of abstraction. When computer engineers are designing processors, they rarely work at the transistor level and instead work with much larger blocks, like logic gates, and even larger components made up of logic gates, which we'll discuss in future episodes. And even if you are a professional computer programmer, it's not often that you think about how the logic that you are programming is actually implemented in the physical world by these teeny tiny components. We've also moved from thinking about raw electrical signals to our first representation of data, true and false. And we've even gotten a little taste of computation. With just the logic gates in this episode, we could build a machine that evaluates complex logic statements, like if name is John Green and after 5 p.m. or is weekend and near Pizza Hut, then John will want pizza equals true. And with that, I'm starving. I'll see you next week. Crash Course Computer Science is produced in association with P.
I need to find the best way to learn math and science.
It's brilliant.
Hi, I'm Carrie Ann, and this is Crash Course Computer Science, and today we're going to talk about how computers store and represent numerical data, which means we've got to talk about math. But don't worry, every single one of you already knows exactly what you need to know to follow along. So last episode we talked about how transistors can be used to build logic gates, which can evaluate Boolean statements. And in Boolean algebra there are only two binary values, true and false. But if we only have two values, how in the world do we represent information beyond just these two values? That's where the math comes in. So as we mentioned last episode, a single binary value can be used to represent a number. Instead of true and false, we can call these two states 1 and 0, which is actually incredibly useful. And if we want to represent larger things, we just need to add more binary digits. This works exactly the same way as the decimal numbers that we're all familiar with. With decimal numbers, there are only 10 possible values a single digit can be, 0 through 9. And to get numbers larger than 9, we just start adding more digits to the front. We could do the same with binary. For example, let's take the number 263. What does this number actually represent? Well, it means we've got 2 100s, 6 10s and 3 1s. If you add those all together, we've got 263. Notice how each column has a different multiplier. In this case, it's 100, 10 and 1. Each multiplier is 10 times larger than the one to the right. That's because each column has 10 possible digits to work with, 0 through 9, after which you have to carry one to the next column. For this reason, it's called base 10 notation, also called decimal, since deci means 10. And binary works exactly the same way, it's just base 2. That's because there are only two possible digits in binary, 1 and 0. This means that each multiplier has to be 2 times larger than the column to its right. Instead of hundreds, tens and ones, we now have 4s, 2s and 1s. Take, for example, the binary number 101. This means we have 1 4, 0 2s and 1 1. Add those all together and we've got the number 5 in base 10. But to represent larger numbers, binary needs a lot more digits. Take this number in binary. We can convert it to decimal in the same way. We have 1 times 128, 0 times 64, 1 times 32, 1 times 16, 0 times 8, 1 times 4, 1 times 2 and 1 times 1, which all adds up to 183. Math with binary numbers isn't hard either. Take for example decimal addition of 183 plus 19. First we add 3 plus 9, that's 12, so we put 2 as the sum and carry 1 to the tens column. Now we add 8 plus 1 plus the 1 we carried, that's 10, so the sum is 0, carry 1. Finally we add 1 plus the 1 we carried, which equals 2, so the total sum is 202. Here's the same sum but in binary. Just as before, we start with the ones column. Adding 1 plus 1 results in 2, even in binary. But there's no symbol 2, so we use 1 0 and put 0 as our sum and carry the 1. Just like in our decimal example. 1 plus 1 plus the 1 carried equals 3, or 1 1 in binary. So we put the sum as 1 and carry 1 again, and so on. We end up with this number, which is the same as the number 202 in base 10. Each of these binary digits, 1 or 0, is called a bit. So in these last few examples, we were using 8-bit numbers with their lowest value of 0 and highest value of 255, which requires all 8 bits to be set to 1. That's 256 different values, or 2 to the 8th power. You might have heard of 8-bit computers or 8-bit graphics or audio. These were computers that did most of their operations in chunks of 8 bits. But 256 different values isn't a lot to work with. So it meant things like 8-bit games were limited to just 256 different colours for their graphics. And 8 bits is such a common size in computing, it has a special word, a byte. A byte is 8 bits. If you've got 10 bytes, it means you've really got 80 bits. You've heard of kilobytes, megabytes, gigabytes, and so on. These prefixes denote different scales of data. Just like 1 kilogram is 1,000 grams, 1 kilobyte is 1,000 bytes, or really 8,000 bits. Mega is 1,000,000 bytes, and giga is 1,000,000,000 bytes. Today, you might even have a hard drive that has 1 terabyte of storage. That's 8 trillion ones and zeros. But hold on, that's not always true. In binary, a kilobyte has 2 to the power of 10 bytes, or 1,024. 1,000 is also right when talking about kilobytes, but we should acknowledge it isn't the only correct definition. You've probably also heard the term 32-bit or 64-bit computers. You're almost certainly using one right now. What this means is that they operate in chunks of 32 or 64 bits. That's a lot of bits. The largest number you can represent with 32 bits is just under 4.3 billion, which is 32 ones in binary. This is why our Instagram photos are so smooth and pretty. They are composed of millions of colours because computers today use 32-bit colour graphics. Of course, not everything is a positive number, like my bank account in college. So we need a way to represent positive and negative numbers. Most computers use the first bit for the sign, 1 for negative, 0 for positive numbers, and then use the remaining 31 bits for the number itself. That gives us a range of roughly plus or minus 2 billion. While this is a pretty big range of numbers, it's not enough for many tasks. There are 7 billion people on the Earth, and the US national debt is almost $20 trillion after all. This is why 64-bit numbers are useful. The largest value a 64-bit number can represent is around 9.2 quintillion. That's a lot of possible numbers, and will hopefully stay above the US national debt for a while. Most importantly, as we'll discuss in a later episode, computers must label locations in their memory, known as addresses, in order to store and retrieve values. As computer memory has grown to gigabytes and terabytes, that's trillions of bytes, it was necessary to have 64-bit memory addresses as well. In addition to negative and positive numbers, computers must deal with numbers that are not whole numbers, like 12.7 and 3.14, or maybe even stardate 43989.1. These are called floating point numbers because the decimal point can float around in the middle of a number. Several methods have been developed to represent floating point numbers, the most common of which is the IEEE 754 standard. And you thought historians were the only people bad at naming things. In essence, this standard stores decimal values sort of like scientific notation. For example, 625.9 can be written as 0.6259 times 10 to the power of 3. There are 2 important numbers here. The 0.6259 is called the significand, and 3 is the exponent. In a 32-bit floating point number, the first bit is used for the sign of the number, positive or negative. The next 8 bits are used to store the exponent, and the remaining 23 bits are used to store the significand. Okay, we've talked a lot about numbers, but your name is probably composed of letters, so it's really useful for computers to also have a way to represent text. However, rather than have a special form of storage for letters, computers simply use numbers to represent letters. The most straightforward approach might be to simply number the letters of the alphabet, A being 1, B being 2, C 3, and so on. In fact, Francis Bacon, the famous English writer, used 5-bit sequences to encode all 26 letters of the English alphabet to send secret messages back in the 1600s. And 5 bits can store 32 possible values, so that's enough for the 26 letters, but not enough for punctuation, digits, and upper and lowercase letters. Enter ASCII, the American standard code for information interchange. Invented in 1963, ASCII was a 7-bit code, enough to store 128 different values. With this expanded range, it could encode capital letters, lowercase letters, digits 0 through 9, and symbols like the @ sign and punctuation marks. For example, a lowercase a is represented by the number 97, while a capital A is 65, a colon is 58, and a closed parenthesis is 41. ASCII even had a selection of special command codes, such as a new line character to tell the computer where to wrap a line to the next row. In older computer systems, the line of text would literally continue off the edge of the screen if you didn't include a new line character. Because ASCII was such an early standard, it became widely used and critically allowed different computers built by different companies to exchange data. This ability to universally exchange information is called interoperability. However, it did have a major limitation. It was really only designed for English. Fortunately, there are 8 bits in a byte, not 7, and it soon became popular to use codes 128 through 255, previously unused, for national characters. In the US, those extra numbers were largely used to encode additional symbols, like mathematical notation, graphical elements, and common accentuated characters. On the other hand, while the Latin characters were used universally, universally, Russian computers use the extra codes to encode Cyrillic characters, and Greek computers Greek letters, and so on. And national character codes work pretty well for most countries. The problem was, if you opened an email written in Latvian on a Turkish computer, the result was completely incomprehensible. And things totally broke with the rise of computing in Asia, as languages like Chinese and Japanese have thousands of characters. There was no way to encode all those characters in 8 bits. In response, each country invented multi-byte encoding schemes, all of which were mutually incompatible. The Japanese were so familiar with this encoding problem that they even had a special name for it: Mojibake, which means scrambled text. And so it was born, Unicode, one format to rule them all. Devised in 1992 to finally do away with all of the different international schemes, it replaced them with one universal encoding scheme. The most common version of Unicode uses 16 bits with space for over 1 million codes, enough for every single character from every language ever used. More than 120,000 of them in over 100 types of script, plus space for mathematical symbols and even graphical characters like emoji. And in the same way that ASCII defines a scheme for encoding letters as binary numbers, other file formats like MP3s or GIFs use binary numbers to encode sounds or colours of a pixel in our photos, movies and music. Most importantly, under the hood, it all comes down to long sequences of bits. Text messages, this YouTube video, every web page on the internet, and even your computer's operating system are nothing but long sequences of ones and zeros. So next week, we'll start talking about how your computer starts manipulating those binary sequences for our first true taste of computation. Thanks for watching. See you next week. Crash Course Computer Science is produced.
This program covers the basics of quantum communication and quantum computing, and it's particularly designed for...
Hi, I'm Carrie Ann and this is Crash Course Computer Science. So last episode we talked about how numbers can be represented in binary, like 00101010 is 42 in decimal. Representing and storing numbers is an important function of a computer, but the real goal is computation, or manipulating numbers in a structured and purposeful way, like adding 2 numbers together. These operations are handled by a computer's arithmetic and logic unit, but most people call it by its street name, the ALU. The ALU is the mathematical brain of a computer. When you understand an ALU's design and function, you'll understand a fundamental part of modern computers. It is the thing that does all of the computation in a computer, so basically everything uses it. First though, look at this beauty. This is perhaps the most famous ALU ever, the Intel 74181. When it was released in 1970, it was the important function is 42 in decimal. Representing and storing numbers is an important function of a computer, but the real goal is computation, or manipulating numbers in a structured and purposeful way, like adding 2 numbers together. These operations are handled by a computer's arithmetic and logic unit, but most people call it by its street name, the ALU. The ALU is the mathematical brain of a computer. When you understand an ALU's design and function, you'll understand a fundamental part of modern computers. It is the thing that does all of the computation in a computer, so basically everything uses it. First though, look at this beauty. This is perhaps the most famous ALU ever, the Intel 74181. When it was released in 1970, it was the first complete ALU that fit entirely inside a single chip, which was a huge engineering feat at the time. So today we're going to take those Boolean logic gates we learned about last week to build a simple ALU circuit with much of the same functionality as that 74181. And over the next few episodes, we'll use this to construct a computer from scratch. So it's going to get a little bit complicated, but I think you guys can handle it. An ALU is really 2 units in one. There's an arithmetic unit and a logic unit. Let's start with the arithmetic unit, which is responsible for handling all numerical operations in a computer, like addition and subtraction. It also does a bunch of other simple things, like add 1 to a number, which is called an increment operation, but we'll talk about those later. Today we're going to focus on the pièce de résistance, the crème de la crème of operations that underlines almost everything else a computer does, adding 2 numbers together. We could build this circuit entirely out of individual transistors, but that would get confusing really fast. So instead, as we talked about in episode 3, we can use a high level of abstraction and build our components out of logic gates, in this case AND, OR, NOT and XOR gates. The simplest adding circuit that we can build takes 2 binary digits and adds them together. So we have 2 inputs, A and B, and 1 output, which is the sum of those 2 digits. Just to clarify, A, B and the output are all single bits. There are only 4 possible input combinations: The first three are 0 plus 0 equals 0, 1 plus 0 equals 1, and 0 plus 1 equals 1. Remember that in binary, 1 is the same as true, and 0 is the same as false. So this set of inputs exactly matches the Boolean logic of an XOR gate, and we can use it as our 1-bit adder. But the fourth input combination, 1 plus 1, is a special case. 1 plus 1 is 2, obviously, but there's no 2-digit in binary. So as we talked about last episode, the result is 0, and the 1 is carried to the next column. So the sum is really 1, 0 in binary. Now, the output of our XOR gate is partially correct. 1 plus 1 outputs 0, but we need an extra output wire for that carry bit. The carry bit is only true when the inputs are 1 and 1, because that's the only time when the result is bigger than 1 bit can store. And conveniently, we have a gate for that, an AND gate, which is only true when both inputs are true. So we'll add that to our circuit too. And that's it. This circuit is called a half adder. It's not that complicated, just 2 logic gates. But let's abstract away even this level of detail and encapsulate our newly minted half adder gate in only next column. But we'll talk about those later. Today we're going to focus on the pièce de résistance, the crème de la crème, XOR gates. The simplest adding circuit that we can build takes 2 binary digits and adds them together. So we have 2 inputs, A and B, and 1 output, which is the sum of those 2 digits. Just to clarify, A, B, and the output are all single bits. There are only 4 possible input combinations. The first 3 are 0 plus 0 equals 0, 1 plus 0 equals 1, and 0 plus 1 equals 1. Remember that in binary, 1 is the same as true, and 0 is the same as false. So this set of inputs exactly matches the Boolean logic of an XOR gate, and we can use it as our 1-bit adder. But the fourth input combination, 1 plus 1, is a special case. 1 plus 1 is 2, obviously, but there's no 2-digit in binary. So as we talked about last episode, the result is 0, and the 1 is carried to the next column. So the sum is really 1, 0 in binary. Now, the output of our XOR gate is partially correct. 1 plus 1 outputs 0, but we need an extra output wire for that carry bit. The carry bit is only true when the inputs are 1 and 1, because that's the only time when the result is bigger than 1 bit can store. And conveniently, we have a gate for that, an AND gate, which is only true when both inputs are true. So we'll add that to our circuit too. And that's it. This circuit is called a half adder. It's not that complicated, just 2 logic gates. But let's abstract away even this level of detail and encapsulate our newly minted half adder as its AND gate, which is only true when both inputs are true. So we'll add that to our circuit too. And that's it. This circuit is called a half adder. It's not that complicated, just 2 logic gates. But let's abstract away even this can store. And conveniently, we have a gate for that, an AND gate, which is only true when both inputs are true. So we'll add that to our circuit too. And that's it. This circuit is called a half adder. It's not that we have AND 1, because that's the only time when the result is bigger than 1 bit can store. And conveniently, we have a gate for that, an AND gate, which is only true when both inputs are true. So we'll add that to our circuit too. And that's it. This circuit is called a half adder. It's not that complicated, just 2 logic gates. But let's abstract away even this level of detail and encapsulate our newly minted half adder as its own component, with 2 inputs, bits A and B, and 2 outputs, the sum and the carry bits. This takes us to another level of abstraction. Oh, I feel like I say that a lot. I wonder if this is going to become a thing. Anyway, if you want to add more than 1 plus 1, we're going to need a full adder. That half adder left us with a carry bit as output. That means that when we move on to the next column in a multi-column addition, and every column after that, we're going to have to add 3 bits together, not 2. A full adder is a bit more complicated. It takes 3 bits as inputs, A, B, and C. So the maximum possible input is 1 plus 1 plus 1, which equals 1 carry out 1. So we still only need 2 output wires, sum and carry. We can build a full adder using half adders. To do this, we use a half adder to add A plus B, just like before, but then feed that result and input C into a second half adder. Lastly, we need an OR gate to check if either one of the carry bits was true. That's it, we just made a full adder! Again, we can go up a level of abstraction and wrap up this full adder as its own component. It takes 3 inputs, adds them, and outputs the sum and the carry if there is one. Armed with our new components, we can now build a circuit that takes 2 8-bit numbers, let's call them A and B, and adds them together. Let's start with the very first bit of A and B, which we'll call A0 and B0. At this point, there is no carry bit to deal with, because this is our first addition. So we can use our half adder to add those 2 bits together. The output is sum 0. Now we want to add A1 and B1 together. It's possible there was a carry from the previous addition of A0 and B0. So this time we need to use a full adder that also inputs the carry bit. We output this result as sum 1. Then we take any carry from this full adder and run it into the next full adder that handles A2 and B2. And we just keep doing this in a big chain until all 8 bits have been added. Notice how the carry bits ripple forward to each subsequent adder. For this reason, this is called an 8-bit ripple carry adder. Notice how our last full adder has a carry out. If there is a carry into the 9th bit, it means the sum of the 2 numbers is too large to fit into 8 bits. This is called an overflow. In general, an overflow occurs when the result of an addition is too large to be represented by the number of bits you are using. This can usually cause errors and unexpected behaviour. Famously, the original Pac-Man arcade game used 8 bits to keep track of what level you were on. This meant that if you made it past level 255, the largest number storable in 8 bits, to level 256, the ALU overflowed. This caused a bunch of errors and glitches, making the level unbeatable. The bug became a rite of
Oh, it just was, I swear.
passage for the greatest Pac-Man players. So if we want to avoid overflows, we can extend our circuit with more full adders, allowing us to add 16 or 32-bit numbers. This makes overflows less likely to happen, but at the expense of more gates. An additional downside is that it takes a little bit of time for each of the carries to ripple forward. Admittedly, not very much time. Electrons move pretty fast, so we're talking about billionths of a second, but that's enough to make a difference in today's fast computers. For this reason, modern computers use a slightly different adding circuit called a carry look-ahead adder, which is faster, but ultimately does exactly the same thing, adds binary numbers. The ALU's arithmetic unit also has circuits for other math operations, and in general, these 8 operations are always supported. And like our adder, these other operations are built from individual logic gates. Interestingly, you may have noticed that there are no multiply and divide operations. That's because simple ALUs don't have a circuit for this, and instead just perform a series of additions. Let's say you want to multiply 12 by 5. That's the same thing as adding 12 to itself 5 times. So it would take 5 passes through the ALU to do this one multiplication. And this is how many simple processors, like those in your thermostat, TV remote, and microwave, do multiplication. It's slow, but it gets the job done. However, fancier processors, like those in your laptop or smartphone, have arithmetic units with dedicated circuits for multiplication. And as you might expect, the circuit is more complicated than addition. There's no magic, it just takes a lot more logic gates, which is why less expensive processors don't have this feature. Okay, let's move on to the other half of the ALU, the logic unit. Instead of arithmetic operations, the logic unit performs, well, logical operations, like and, or, and not, which we've talked about previously. It also performs simple numerical tests, like checking if a number is negative. For example, here's a circuit that tests if the output of the ALU is 0. It does this using a bunch of OR gates to see if any of the bits are 1. Even if one single bit is 1, we know the number can't be 0. And then we use a final NOT gate to flip this input, so the output is 1 only if the input number is 0. So that's a high-level overview of what makes up an ALU. We even built several of the main components from scratch, like our ripple adder. As you saw, it's just a big bunch of logic gates connected in clever ways. Which brings us back to that ALU you admired so much at the beginning of the episode, the Intel 74181. Unlike the 8-bit ALU we made today, the 74181 could only handle 4-bit inputs, which means you built an ALU that's like twice as good as that super famous one with your mind. Well, sort of. We didn't build the whole thing, but you get the idea. The 74181 used about 70 logic gates, and it couldn't multiply or divide, but it was a huge step forward in miniaturization, opening the doors to more capable and less expensive computers. This 4-bit ALU circuit is already a lot to take in, but our 8-bit ALU would require hundreds of logic gates to fully build, and engineers didn't want to see all that complexity when using an ALU, so they came up with a special symbol to wrap it all up, which looks like a big V. Just another level of abstraction. Our 8-bit ALU has two inputs, A and B, each with 8 bits. We also need a way to specify what operation the ALU should perform. For example, addition or subtraction. For that, we use a 4-bit operation code. We'll talk more about this in a later episode, but in brief, 1000 might be the command to add, while 1100 is the command for subtract. Basically, the operation code tells the ALU what operation to perform, and the result of that operation on inputs A and B is an 8-bit output. ALUs also output a series of flags, which are 1-bit outputs for particular states and statuses. For example, if we subtract two numbers and the result is 0, our 0 testing circuit, the one we made earlier, sets the 0 flag to true. This is useful if we are trying to determine if two numbers are equal. If we wanted to test if A was less than B, we can use the ALU to calculate A subtract B and look to see if the negative flag was set to true. If it was, we know that A was smaller than B. And finally, there's also a wire attached to the carryout on the adder we built. So if there is an overflow, we'll know about it. This is called the overflow flag. Fancier ALUs will have more flags, but these 3 flags are universal and frequently used. In fact, we'll be using them soon in a future episode. So now you know how your computer does all of its basic mathematical operations digitally with no gears or levers required. We're going to use this ALU when we construct our CPU 2 episodes from now. But before that, our computer is going to need some memory. We'll talk about that next week. Crash Course Computer Science is produced in association with PBS Digital Studio.
Alright. Figured out a way to kind of work here. I'm gonna have to turn that up because I can't see as much. There we go. That's where we're at. Bugging. Cool. I'm tired. These are hard, man. Chair just popped. It's great. Sleeps if I'm leaning back, so it's gonna be weird, but it's asking. But that's okay.